A quick solution to LeetCode 155 min stack. So design a stack that supports push, pop, top, and retrieving the minimum element all in constant time. Implement the min stack class. Min stack initializes the stack object. Void push pushes the element into the stack. Pop removes the element. Top gets the top element. And get min retrieves the minimum element in the stack, all of which must run in O of 1, so all of it must run instantly. So first of all, looking at this problem, we can see that a normal stack's behavior will fulfill push, pop, and top. But a normal stack cannot cannot perform get min in O of 1 time, right? It doesn't necessarily know what the minimum in the stack is. So the first thing you might think of is to simply use a variable to store all of the items that we push into our stack. And this variable would just be, for example, int, it would be the running minimum, and we would update it every time we see a smaller value. However, the problem with this solution is that it doesn't work for when we pop out of the stack, right? For example, if we have 5, 4, 3, all of a sudden, when we push 5, it's 5, the running minimum is 5, then it's 4, then it's 3. But then after we pop 3, we no longer know what our current minimum is anymore. So we need a way to store a multitude of running minimums. So how might we go about that? One of the best approaches to solve this problem is to simply use 2 stacks. So one stack is going to represent our actual stack. It's going to be the normal pushing everything in, popping everything out, getting the top. It's going to represent our normal stack. And then we're going to actually hold another declare another stack. This stack is going to be our running minimums. So we see why this approach is sort of intuitive, right? Previously, we were unable to keep track of our running minimums. Now we're just going to keep track of our running minimums. And how might this work? So I drew this example down here. So every PU represents pushing, and every PO represents popping. So what this would sort of look like is we would push 5. So in our stack, we would first see 5. Is this 5 a running minimum? Yeah, it is, right? We see that 5 is the smallest number because it's the only number in our stack. If we were to call get min, we would return 5. So it is a running minimum. However, if we called something instead like top, we would just use our normal stack. Whenever we call top, we always just retrieve from our normal stack. Whenever we need to retrieve the get min, we always retrieve from our running minimum stack, and that makes sense, right? And then we'll see in a sec when we need to push to our running minimum, and when we need to push to our normal stack. So now we see 4, we push it to our normal one. Is 4 a running minimum? Yes, it is, right? 4 is smaller than 5. We want to keep track of that as well. And then 3. So we just keep on going, and then we push 3 again. We keep on going. Is 3 a running minimum? Well, 3 is equal to 3 here, but 3 is still a running minimum, right? In case we can think about it this way. If we were to later on have to delete this 3, like after we add this 3, we would need to know that the minimum is still 3. The minimum in our stack is still 3. If we didn't add this 3 now, we wouldn't know later on if the minimum was still 3, right? So of course we have to add that. And then we see 7. Is 7 a running minimum? No, it's not. So we do not add it to our running minimum stack, but we do add it to our normal stack. Our normal stack just has the normal behavior. See, now if we use call top, we still call 7, but if we call get min, the smallest item in our stack is still just our 3. So our running minimum should take the form of a monotonically decreasing stack, right? Every time we add an item, it must be smaller. We're not strictly decreasing, monotonically non-increasing, I guess you can say, if that is a thing. So this stack, the bottom items have to always be bigger or equal to its adjacent higher item, right? So it needs to have this descending behavior for it to keep track of running minimums, because every time we call get min, we're just going to be using this top item in our stack, which will represent the smallest item in this current big stack, the actual stack. So after pushing 7, now we want to pop. We pop 7, we get rid of it like normal, right? This is just a normal stack. We will always just do normal behavior on it. So when we pop 7, we see, was 7 one of our minimums? Or was 7 our minimum? No, it wasn't, right? That means that we don't need to change anything in running minimums. Same thing for 3. Let's take a look at 3. We pop 3, we see 3 is our running minimum. We must get rid of 3, right? And then we go on to the next one. We pop again, so we pop 3, and then we see is the running minimum, we call get min, is get min equal to 3? Yeah, it is. So we get rid of that top one in this running minimum stack. And then we move on to the next one, push 2. Is that a running minimum? Yes, it is. Push 3. Is that a running minimum? No, it isn't. Does not belong in running minimum, but it does belong in our normal stack. Pop. So pop 3. Our current running minimum is still just 2, right? And we don't need to get rid of anything here because it wasn't a minimum. And then same thing over here. We pop again. We get rid of both. And then so at the end, we would have a stack that sort of looks like this. And they both just represent, so this left side will always just represent the normal stack. So it's just a normal stack. Whenever we call one of the first 3 methods that I shared earlier that retain, these first 3 methods that retain to a normal stack are going to be, we're going to call on our normal stack. And then for this last get min, we're going to call on our newly added running minimum stack. So when we declare this min stack object, we actually have 2 stacks in the abstracted away in the back end doing work for us, allowing us to compute everything and do everything in O of 1.